Okay, hey, this time I'm going to follow up on the Thévenin equivalent circuit videos with a Norton equivalent circuit video. This should be a quick addendum because this is such a dual concept or homogeneous concept. So a Norton equivalent circuit is extremely similar to a Thévenin equivalent circuit. It's just that the Norton model employs a parallel current source rather than a series voltage source. So if you've done all the work to calculate a Thévenin equivalent, you actually already also have the Norton equivalent. It's just that you may choose to model it either way. So you're not actually doing any extra work. You don't need to do any extra work. If you've calculated one, you've calculated the other. It's just that there's two different ways of thinking about the same model. So let me explain what I'm talking about. This is the box that I drew 2 videos ago when I introduced the concept of a Thévenin equivalent circuit. You have sources and resistances inside this box. You have terminals that you're looking at that have some open circuit voltage and a short circuit current. If you connect them, there's a Thévenin equivalent resistance looking in. And so now I'm going to say, now I'm going to introduce the concept of the Norton equivalent. So the Thévenin resistance applies whether or not you're drawing a Thévenin or Norton equivalent. So the Thévenin resistance is the Norton resistance. They're the same thing. And to refresh, the open circuit voltage is the Thévenin voltage, right? And in the same way, the short circuit current is the Norton current. And once I draw the circuit, it'll make total sense. But just to lay down some definitions quickly, again, so the Thévenin resistance is the Norton resistance. They're the same thing. And it's the ratio of the Thévenin voltage to the Norton current, which is equivalent to the open circuit voltage divided by the short circuit current. So that means that the Thévenin voltage equals the open circuit voltage and the Norton current equals the short circuit current. All these things are equivalent. So let me quickly draw the example circuit that I've used several times now in the past few videos. So I have a 100 ohm resistor and a 50 ohm resistor in series with this a 10 volt source. And I'm going to draw this dashed box around this. And like I showed in the previous videos, the Thévenin equivalent for this circuit looks like this. We found that a 5 volt independent voltage source with a 33.3 ohm resistor in series equivalently modeled this circuit in the box. So the beauty is, rather than modeling this with a voltage source in series with the Thévenin resistance, we could actually model this with a current source in parallel with the Thévenin resistance, and it will describe this circuit in the same way. And we actually already have all the information we need. We already know the Norton current, which will be the value of that current source, and it's the short circuit current that we already found, that we already used to compute this voltage and current. So we can just automatically draw this model. And it looks like an independent current source like this in parallel with a resistor, which is the Thévenin resistance or Norton resistance. Again, they are equivalent. 33.3, that's 33.3 ohms. 0.15 amps, like we computed in a previous episode. And then we have our terminals coming out here. And let me draw a dashed box around this like that. So, again, guys, everything within these dashed boxes, these are equivalents. This is our original circuit. This is an equivalent Thévenin model. And on the right, we have an equivalent Norton model. Let me write this out. So we have our original circuit. We have our Thévenin equivalent circuit, and we have our Norton equivalent circuit. So these models both describe this circuit. Given that you interacted with this port, this Thévenin model or this Norton model could be inside, and you would not know the difference between these two or either of these two and the original circuit. You would not know. So this could be arbitrarily complicated inside, yet you can model it with something as simple as a single source and a resistor, a single voltage source and a resistor, or a single current source in parallel with a resistor, voltage source being in series. You can see how the Thévenin resistance is 33.3 ohms, or it's the same in both models, but what differs is the value of the voltage source or the value of the current source, and you can see that this voltage and current are related to each other via Ohm's law through this resistor, right? So just think about that to yourself for a second. Think about how this current source creates the open circuit voltage across the resistor when they're in parallel, and think about how this voltage source creates the short circuit current through this resistor when they're in series. And so that's all this is, this concept of equivalent models, Thévenin and Norton. It's very simple when it comes down to it, but it's important that you understand what's going on here. I hope this was helpful, and again, let me know if you guys have any questions or if there's any way I can improve these videos. Again, thank you for watching, and I hope you have a great day.